3.8, we're going to talk about exponential equations. So exponential equations, it's going to be very similar to what we've seen before as far as the exponential sequences that we talked about. We're going to quantify them and actually make them into equations now instead of just sequences. So what we're going to do here for A through D is we're going to match the equations to the graphs below. Okay? So if I look at A, the first thing I'm going to do is I'm just going to plug in some random point and see that if it's on the graph here. Because we know if we have a true statement, then we're going to get a point on one of these graphs, right? On one of these lines. So let's plug in 0 for x for this one. So if I have 0 for x, I plug in 0. What do I get for y? Well, 1/4 to the 0th power is 1, so y is 1. Okay. So do I have any of these graphs that have 0, 1 as one of our solutions? Well, if I look at it, it looks like the only one is 2 right here. So 0, 1 is on that, but it's not on this one, it's not on this one, and it's not on this one. So I know that 2 is my solution for A. And then let's look at that graph just a little bit more. So I have a 1/4 right here, and I notice that the graph kind of curves down and then to the right like that. So just keep that in mind when we're looking at other ones, like when we're looking at this one. This one isn't a fraction anymore, right? It's greater than 1. So let's look at B. What if I plug in 0 for x for here? So I have 0 for x. 3 to the 0th power is 1. 1 times 10 is 10. So y is 10 here. So that's one point that I have on here. And it looks like the only graph again that goes through that point is 3, 0, 10. So this is my graph for B. So notice how I have a 10 here. So I have a 10 here and a 10 here. And notice how that number appears on the graph here as our y-intercept. Sorry, down here. This should be B rather. So notice how that crosses the 10 there. Okay? Alright, and then notice the shape of the graph. So this time we have a number greater than 1, and that'll be important. I'll explain here why in a second. And see how it goes up like that. So it's kind of going from the left and going up, whereas the one before went down from the left and kind of went right. Okay? Alright, C, it says we have 7 times 2 to the x. I'm just going to plug in 0 for x again. So I get 0, 2 to the 0 is 1, 1 times 7 is 7. So y is 7. And it looks like the only graph that crosses 7 is 1 right here. So C is the first graph. Okay? And notice how this is a whole number, or this is a number greater than 1 again. And notice how it similarly mimics what B did. So they look pretty similar as far as the shape of the graph. And then finally that means D goes to the one down here. So notice how this crosses the 6 over here on the y-axis. And notice how the multiplier out front here is a 6 as well. So that'll be important. And then we see that this 1/3 to the x power, it mimics the graph kind of like A did. So A and D are pretty similar as far as the graph that they show, where it kind of goes down and to the right, down and to the right. Okay? Alright, so my question A is, where does the starting value in the exponential function appear? Well, it's just the coefficient of the multiplier. So what is that? What is the coefficient of the multiplier? Well, if we look at these up here, this is the coefficient, this number 10, and the multiplier is just this 3 to the x power. Okay? And then similarly over here, this is our multiplier, this is to the x power. But what's our coefficient here? When we don't have one listed, we just assume that we're multiplying that by 1. So our coefficient here is 1. This one, our coefficient's 7. We're multiplying by 2 to the x. So 7 is where it crosses the graph. And then 6 over here. So that's where it crosses the y-axis. That's always our starting value. So we see right here, here, and here. All right? Alright, the next one says, describe the value of the multiplier when the graphs look like they're increasing. So like this one right down here. Well, the multiplier when our graphs are increasing like that, they are greater than 1. So I'm going to say m, our multiplier, is greater than 1. So our multiplier is greater than 1. Describe the value of the multiplier when the y values are decreasing. So they look like this. Well, that's when the multiplier is less than 1. The multiplier is less than 1, but the multiplier is also greater than 0. So it's just between 0 and 1. And then the graph will look like it's decreasing here. Okay? So every one of our exponential functions takes this form right here. So we have our form, I'll write it a little bigger, y equals a, where a is just our coefficient out front, multiplied by b, which is our multiplier, raised to the x power. Okay? So if a is greater than 1, so our multiplier m is also a here. If it's greater than 1, then it's going to look like this graph. If it's between 0 and 1, it's going to look like this graph. Okay? Or I guess, it's b for our multiplier there, I apologize. b is our multiplier here. A is our coefficient, that's our starting position. Alright, so if we look at the graphs down here just quickly, we see that we have 2 for our starting value. So this is kind of like the y-intercept and our slope-intercept form. So we have our 2 right there that crosses the y-axis. And then similarly, for this one, we have 4 as our starting value, so it's going to be right there. Okay. And then this is between 0 and 1, so we have this decrease. And this is greater than 1, so we have an increase. Okay. So what if we suppose we have a y is an exponential function, so it's going to take the form of y equals a times b to the x, okay, with an initial value of 7 and a growth rate of 10%. So my initial value, remember that is a, so a equals 7. And if we have a growth of 10%, if we change that into a multiplier that we can use in here, that should be 1.1. Right, because we just add 1 to it. So that's our multiplier. So we can just plug those two values in, and we get y equals 7 times 1.1 to the x power. Okay. On the next one, if we suppose y is an exponential function of x with an initial value of 7 and a decay rate of 10%. So this is like a 10% discount. 10% discount. Well, our initial value, a, is 7 again. And then if we have a 10% discount, we know that's 90% of the price. So our multiplier here, b equals 0.9. Okay? So we just plug those two into this formula again. We get y equals 7 times 0.9 to the x. Okay? All right. Let's look at the next one. So the next one says, for each exponential function, state the following and then graph the function. So I've already graphed the functions for us, but let's look at this one. So if the function represents exponential growth or decay, so let's do that for both of them first. So this one, we have this graph that kind of goes up. So we can kind of see it kind of goes out this way and then it goes up like that. So this one shows growth because your values are getting bigger and bigger and bigger. So this is just like our linear growth, but it's exponential this time. So it's getting bigger and bigger and bigger. Okay. So this one, this graph right here, that corresponds to this is exponential growth. Okay. If the value is increasing or decreasing, if it's exponential growth, growth is increasing. So it's increasing. Okay. What is the starting value? So the starting value is just where it crosses the y-axis. In this case, it's 0, 8. Okay. What's the multiplier here? The multiplier is just 1.1. It's whatever is being raised to the x power. So I'm going to say b equals 1.1. Okay. And then I'm going to skip the rate of change. but then I'm going to look at 2 points on the graph. So I already have 0, 8, right? So let's do the other point that's on the graph. Well, this is 1, 9. So the other point on the graph is 1, 9. Okay. All right, and then let's look at the next one, and we're going to do the same thing. We're going to do those 6 again, or those 5 rather. So the function showing exponential growth or decay. Well, this is going down and to the right, right? It's getting smaller and smaller and smaller. So this one is exponential decay. Okay. If the function is increasing or decreasing, it's clearly decreasing, right? If it's decay, it's decreasing. It's decreasing. What's the starting value? 0, 5, right? And we can definitely tell from the formula we have that 5 right there. So 0, 5. Okay. What's the multiplier? It's whatever's being raised to the x power, so it's 1/2 in this case. So it equals b. Okay. And then finally, one more point on the graph, right? We're looking for 2 total. So we have one right here, and another one. Looks like maybe 1 and 2.5. So 1, 2.5. So I just guessed right there, or I guess I already knew what it was. But if I wanted to find that point, well, I know that x is 1 there, right? Like I can definitely tell x is 1 right there, but I don't know what this value is. So how can I find that out? Well, what if we just plug 1 into this equation? If we plug 1 in for x, we get 1/2 to the first power, which is 1/2. 1/2 times 5 is 2.5, right? And you can check that with other ones too, if you wanted to plug 2 in there, or 3, or 4, or 5, or whatever number you wanted to put in there. All right. So let's look at some more realistic examples. So this one says, in recent month, the app brought in $43 million in revenue after Apple and Google took 30% of its revenue. How much revenue did the app earn before paying Google and Apple? So this one, the app that we're talking about is Candy Crush Saga, by the way. So if they took in $43 million in revenue after Apple and Google took 30% out, how much revenue did the app earn before paying them? So I want to kind of increase this by some amount, by 30%, right? So the way I'm going to write this is the $43 million that they got is equal to, and 30%, we can change that into a multiplier, right? So that's like a 30% decrease since they're taking it out. So I can change this into a multiplier of 0.7. Okay? So that 43 million that they had is equal to 0.7 of their total revenue. Okay? So 43 million is 0.7 of their total revenue. So I'm just going to solve for R to find out how much revenue they actually had before they gave it some away to Apple and Google. So let's divide everything by 0.7. Okay? So R is going to be equal to, I'm just going to do 43 divided by 0.7 on my calculator. So 43 divided by 0.7. And I'm getting 61.43 million after I rounded to the 100th place. Okay? So that's how much revenue they brought in before they gave some of that away to Apple and Google. Okay? All right. So I'm gonna skip this part right here. I'm just gonna move on straight to B here. It says if the app has been downloaded 500 million times already and it gains 8 million new downloads per month, write a linear model. So it's this form right here, y equals mx plus b, to represent the total number of downloads, or the number of downloads at any certain month. So it says let d be the number of downloads in millions and m be the number of months. So in this case, D, the number of downloads, should be for Y. So we'll sub those two between each other. And then M is the number of months that have passed. So that's our X value. Okay. All right. So I know that there's been 500 million. So I'm going to write 500, and I'm just going to say that these are going to be in millions. So I can work with some smaller numbers. So this is in millions. So 500 million is equal to M. Well, what do we know for M? Well, M is the slope, or the change, right? And we know we're changing, we're gaining 8 million new users. So M is 8 million. X, well, do we know X? We don't yet, right? We just know it's M. And actually I messed that up, I'm sorry. So D is the number of downloads that we have, right? So the number of downloads that we have equals, well, we're getting 8 million per month. And then we can add to that the 500 million that we already have, right? So that should be our solution. Okay? Alright, so now that we've made that, now we can do the same thing for C, right? So this one says if the app has 500 million times, has been downloaded 500 million times already, and the number of downloads grow at 2% each month, it says write an exponential model, so it's in this form right here, to represent the number of downloads using the same variables as part B. So I'm going to keep downloads the same. So my downloads equals, what is my A? Well, that's my starting or my initial value, right? We start at 500 million. So I'm going to write 500 again and just assume this is in millions again. In millions. Okay? And then I'm going to multiply that by B. Do I know what my B is? Well, that's a 2% growth. So 2% as a multiplier is 1.02. So 1.02, that shows my 2% growth. And I'm going to raise that to the M power, right? Because our X here is M in this case, representing the number of months. Okay. All right. And then part D, it says use each model to predict how long it will take to reach 1 billion downloads at the rate stated. So I'm going to omit that for part C. I think that's a little bit beyond the scope of this course, but we will do it for B. So I know that my downloads is 1 billion or 1,000 million, if you want to put it that way. And that equals 8 times the number of months plus the 500 million that we already have. So all I'm doing is just substituting in the 1 billion for D here. Okay? And then now I can just solve for how many months it'll take. So I'll subtract 500 on both sides. So I get 500 equals 8M. And then I'll just divide by 8 on both sides after that. So divide everything by 8, we get M, so the number of months it'll take, and you should get about 62.5 months. So it'll take about 62.5 months to get to the 1 billion downloads with the with part B. Okay. All right, and then I'm gonna, like I said, I'm gonna omit part C for that one. Okay. All right. Now on to the last example here. So this one says, so we kind of have a table. It says complete each table of ordered pairs assuming an exponential change and write a function to represent the relationship shown in the table. Okay. So this one right here, every time we've seen a table, we always count up by 1 with the x's. So I'm going to continue that trend. So I'm going to kind of go backwards here, then I'm going to go forwards. Okay. So we're just increasing and decreasing by 1 every time for x. Okay. All right. So we know that this is an exponential change. So I know it's going to be in the form of y equals a times b to the x. Okay. And the only thing I know is I have 2 different points that form this right here. So I'm going to fill in what information I do know with these 2 points. So I know my x and I know my y, right? So I'm going to plug those 2 in. So I'm going to get 54 for my y equals a times b to the second power. Okay. So I can't really do anything with this yet, right? So I have 2 different variables and there's not really an easy way to solve for them yet. So the next thing I'm going to do is I'm going to plug in these 2 values, okay? So I have 4,374 equals a times b to the 6th power, okay? So now what can I do? Well, I have these 2 things that look very similar, right? They almost look like the same thing except for the different numbers that I plugged in. So what I'm going to do is I'm actually going to just divide each one of them, divide this one by the smaller one. So the reason that I'm dividing the bigger one by the smaller one is because when I divide these b's, I'm going to get b to the 4th, right? So I want to deal with whole numbers for my exponents that aren't negatives. So I'm going to take this whole thing and divide this by it. So this whole thing divided by 54 that equals a times b to the second power. Okay? All right, so on the left side, I'm going to have 4,374 divided by 54. And if I do that, I should get 81. I should get 81 on the left. So this divided by this, I get 81. And this equals a divided by a, which is 1. So those will just cancel. B to the 6th divided by b to the 2nd. When we're dividing exponents, when we're dividing the same bases with different exponents, we subtract the exponents. So 6 minus 2 is 4. So we get b to the 4th on the right side. Okay? So 81 equals b to the 4th. So how do I undo that 4th power? Well, I just take the 4th root on both sides. Okay? So I get b equals 3. Okay? So I know my b is 3. If I know what b is, why don't I just plug that back into this one right here, and then we can find out what a equals. Okay? So I have 54 equals a times 3 to the 2nd power. Okay? So 3 to the 2nd power is 9. So I'll divide both sides by 9. So on the right side, I'm just ending up with a. And on the left side, 54 divided by 9 should be 6. So I know that a is 6 here. Okay? So I have my a and I have my b. So my equation here should be y equals 6 times 3 to the x power. Okay? So that's my function or my equation for this one. Okay? So I know that 6 is my starting value, right? So 6 for my starting value should be where this one goes right here, since x is 0, right? It's my starting value, 6. And I know that I'm changing by 3 every time. So with this table, I'm just going to multiply by 3 every time, right? And this kind of checks our answer to make sure we did it right, because as we go down here, if we multiply by 3 every time, we should reach this number at the end that we're already given. So 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. 162 multiplied by 3 is 486. And then 486 multiplied by 3 is 1,458. Okay? And this makes sense, right? So we have this exponential growth, so we're kind of getting bigger and bigger. And we also have a whole number here, right? So we can kind of confirm that we're definitely growing. Okay? All right. Let's look at this last example here. So this last example, I'm going to do the same thing I did up here. And I'm going to substitute x and y in here and substitute x and y in here. So the two equations I should get is 4 equals a times b to the first power. So I'm just substituting x and y in. I'm going to do the same thing for this one. So I have 1/4 equals a times b to the third power. Okay. Then I'm going to divide both sides by the smaller power of b, which is this one. So I have 4 divide that by 4 equals a times b to the first power. Okay. So the a's will cancel again because those are both just to the first power. B to the third divided by b to the first, subtract the exponents, we get b squared. And that'll equal 1/4 divided by 4 should be 1 over 16. Okay. And then I can undo the square b squared by square rooting it. Okay. So when we have the square root of a fraction like this, what we can do is we can just take the square root of the top and take the square root of the bottom. So the square root of 1 over the square root of 16. So the square root of 1 is just 1. And the square root of 16 is 4. So I'm changing by 1/4 each time. So I should see that I'm changing by 1/4 each time. Okay. Alright, so now we can plug that into one of these equations up here, right? And I'm just going to do this one since it's just b to the first. It should be a lot simpler. So I have 4 equals a times 1 over 4. I'm just substituting that in for b. And we should have a times 1/4. So I'm going to divide everything by 1/4. So just to get a by itself. So dividing by 1/4 is the same thing as multiplying by 4 on both sides. So we should get a equals 16. A should equal 16 after we divide by a fourth or multiply each side by 4. Okay? Alright, so a is always my first value. And I guess I forgot to mark these. So I'm just adding 1 each time to x. Okay? So if we divide this by 4 or multiply it by 1/4, we get 4. Multiply that by a fourth or divide it by 4, we get 1. And then 1 divided by 4 multiplied by 1/4 is 1/4. And then we should get 1/16 is the last one. Okay? So then, now that I have my table filled in, I'm going to create my function here. So I have y equals, I know that a is 16. Multiply that by 1/4, which is my b. Raise that to the x power. Okay? That's my function for that one right there.